Welcome to the second lesson of a topic titled Power Functions with Modeling. Lesson 2b is all about general power functions. We'll do a power function analysis on the square root of x, or x to the 1/2. We'll also learn about planetary motion by generating the power function used in Kepler's third law. I'm Mr. Stark, and this is Polynomial and Rational Functions. Let's get analytical. Let's start this lesson with a power function analysis. In lesson 2a, we analyzed the cube root of x and 1 over x squared. Now we'll analyze the square root of x, or x to the 1/2. Here's a simple graph of the square root of x, and I want you to notice that it's the top half of a horizontal parabola. If you take calculus in the future, it's helpful to know this because the slope of this function at the origin is undefined. The domain of this function is 0, infinity, inclusive of 0. Just to clarify, the square root of 0 is 0. The range of this function is also 0, infinity, inclusive of 0. This function is always continuous, and even though it doesn't include any negative x values or finish the parabola below the x-axis, we consider it continuous on its domain. The square root of x is also always increasing. The larger the x values you input, the larger the y values will be as outputs. It has no symmetry about the y-axis nor the origin. However, it is bounded below by the x-axis. There is no max, but it does have a minimum at x equals 0. Side note, a function can be bounded below and not have a minimum, like 1 over x squared, or bounded below and have a minimum, like the square root of x. The square root of x doesn't have any asymptotes, horizontal or vertical. Finally, the end behavior. The limit as x goes to infinity of the square root of x is equal to infinity. I'd like to point out that the square root function is a good model for our heights as humans. So even though we study it in algebra, pre-calculus, and calculus in a very mathy way, it's nice to know it has a very practical purpose. Now let's talk about planetary motion. The data that we have in front of us includes information about 6 of the planets. Huh? That's weird. Who turned out the lights? It must have been the ghost of Johannes Kepler. Of course he's interested in what we're doing. Did you know that he was a noted astronomer who developed 3 laws of planetary motion that are used to this day? Kepler's third law, which we'll generate in just a moment, states that the square of the period of orbit, t, for each planet is proportional to the cube of its average distance, a, from the Sun. The average distance from the Sun in gigameters is provided in the second column, and the period of orbit in days is provided in the third column. Our goal is to use this data to obtain a power function model for orbital period as a function of average distance from the Sun. In other words, we'll model the data using a power function such that average distance from the Sun is the independent variable, or list 1, and period of orbit is the dependent variable, or list 2. Then we'll use the model to predict or regress the orbital period for Neptune, which is 4497 gigameters from the Sun on average. So let's start modeling. On the graphing calculator, that is. So the first thing we'll do is go to the stat edit screen where we could enter the data. And don't worry if you don't have the data, I have it for you. But I have data in here that I want to clear. So I press stat, option 4 for clear list, and it'll take me to the main screen, and I choose second 1 for list 1. That's in blue. Press enter. And then I press second enter to pull up the previous line and change the L1 to L2. And then press enter. So now we could go back into stat edit and enter our data. And I'll probably be entering this quicker than you can, but follow along, and you can pause the video as we go or when I'm done entering the data. I could enter this pretty quickly because I'm on the computer. So those are all the x values, the average distances, and then notice this third one is the period for Earth, 365.2325 days. So now is a good time to pause. The next thing we'll do is see what this data looks like. So go to y equals, I clear out this function I have, and I have my plot 1 on. If yours isn't on, you just hover over plot 1, press enter. Then I'm pressing zoom stat. I've shown that in a previous video before, and we can see our data here. Automatically adjust the window based on our data, which is super convenient. So that's the scatter plot of our data. And you know, it doesn't seem like the greatest, but what we'll do now is model it. So stat calc takes us to this window. Notice we have linear, quadratic, cubic, quartic, ln, natural log, exponential, and then option A is power regression. So that's what we want to use here. Verify that list 1 and list 2 is what we used. It was in my list. And we'll store the regression equation as y1, or whatever function we want to do. So alpha trace gets us there. Press enter. Then press enter a few more times, and it will calculate the model for our data. So we're kind of halfway there. And there's our model at the top. You might not have the r squared and r at the bottom. Those are correlation coefficients, which the closer they are to 1, the better our data is modeled by that function. So going into y equals, we can see that this has a lot of decimal places to our equation, and we'll simplify this in just a moment. But I want you to see that the power is pretty close to 1.5. And we could press second left to go back to the beginning of the line. And the coefficient is really close to 0.2, which is 1/5. Graphing that, we can see that the curve models our data quite well. So, hey, this is a pretty good model for the planets, their average distance to the sun, and the orbital period. So the next thing we'll do is write out that equation and manipulate it a little so that we could compare it to what Kepler's third law of planetary motion is. The model that we just found rounded to 1 decimal place is y1 equals 0.2 x to the 1.5. y1 represents the period of orbit in days, which in the problem situation was defined by the variable t. The variable x represents the average distance from the sun in gigameters, which in the problem situation is defined by the variable a. Therefore, I could rewrite that equation as t equals 1/5 a to the 3/2, because 3 divided by 2 is 1.5. And we can rewrite that as t equals 1/5 square root of a cubed. We're getting really close to the original statement. Now let's square both sides to undo the square root. So we get t squared equals 1/25 times a to the 3rd power. There, I think we have it. This is Kepler's third law. It states that the square of the period of orbit, t, so t squared, for each planet is proportional, so that proportion is 1/25, to the cube of its average distance a, so a cubed from the sun. That is out of this world! Now let's use that model to predict the orbital period for Neptune, and we'll go back to the calculator for that. So I'm back on the screen where we left off, and we have this goal of predicting the orbital period for Neptune at 4497 gigameters as the average distance from the sun. So let's press second trace, and we could enter this value and see it graphically. So type in 4497, and let's see what happens. Oh no, there's an error. It says invalid. Let's go to it. The problem is that this window doesn't include that number, 4497. By pressing on the window, we could see that. So we could increase this x max to include that value, but we don't necessarily know what the y max will be. So entering 5,000 will allow for some wiggle room there, but let's not even do that yet. Second mode goes to the main screen, and let's simply enter the 4497 into the function. Using alpha trace, we choose y1, and enter it in using function notation. That way we don't have to worry about the window that our graph has. So we get the answer is 60,150 days. Wow, okay. We would have been way off. But if we really want to see it, we could go back to the window, keep that 5,000 for x max, and change the y max to something bigger for sure than 60,150. So I like to go a little more than usual. So this doesn't really help, but if we go back to second trace and enter our value, then we can see it pop up on the screen. 4497, and now that allows us to enter that information. So this just confirms what we already knew, but at least we could see it, and we could see it show up on the curve and verify that it makes sense with the model. Well, I think we've reached our goal. Not only did we generate the model for Kepler's third law of planetary motion, we used it to find the orbital period for Neptune. Nice job. That's the end of the second topic of the polynomial and rational functions unit. I'm Mr. Stark. Join me for the next lesson, lesson 3a. Did you press that subscribe button yet? Give me a thumbs up if you liked the video. If you have a question, you might as well ask it. Do you have a comment? Feel free to add it. Hey, thanks for watching.